Okay, hello everyone. My name is Nondh Panithanpaisal. My last name is very long because I'm from Thailand. So bonus points for anyone who can say my last name correctly. Um, right now, I'm a graduate student at University of Pennsylvania, working with Robin Sanderson. And today, I'm excited to tell you about how to use stellar streams in action and angle space to try to constrain the dark matter halo symmetry axis. And by the symmetry axis, I would mean just the minor axis in this case, or the axis with the smallest eigenvalue. So let's get started. So just to set a stage, there are many evidences that the dark matter halo of the Milky Way are twisted and tilted, meaning that the direction of the minor axis of the dark matter halo are not perfectly aligned at all radii. So on the left-hand side, I show you a plot from one of the simulations from the Fire 2 suite, M12 in this case, where I try to plot the misalignment angle, which is just the angle between the minor axis of the dark matter halo at each radius and the direction of the total angular momentum of the disk of the galaxy at different radii. So we see the mismatch starts off around like 10 degrees at like 10 kpc, but this value goes up to like 50 degrees at like 100 kpc. And on the right hand side, I'll show you some estimates that people have made for the location of the minor axis of the Milky Way halo using many different traditional methods. Like the ones where people use stream, they probably just do some kind of orbit fitting to try to constrain the potential. Like the first two, they were using Sagittarius stream. The third one, they were inferring the direction of the minor axis from the plane of satellites. And the last one, if I remember correctly, they were using the Orphan stream. So now the question that I'm trying to answer is if there is any complementary or like alternative way to use stellar stream to constrain the symmetry axis. And so we will turn into the action angle and frequency space, which Fanik introduced to you like a little bit earlier. Like in this case, we can represent stream in real space on the left-hand side. And this one is in the projected X versus Z axis. This one is a very long and convoluted stream. And assuming a potential, we can do a canonical transformation from the real space on the left-hand side to the action, angle, and frequency space on the right-hand side. But in this work, we will be focusing on only in angle and frequency space shown on the right-hand side. So a convoluted stream on the left appear as just line over densities in the angle space and the frequency space. So how can we make use of these line over densities? So the idea has been developed by Jason Sanders in his 2013 paper, where if we assume the correct potential, then the slope of the line in the angle space and the slope of the line in frequency space should match up perfectly. However, they pay attention more on like the shape of the halos and the overall like the parameters, fiddling with the parameters of the potential model itself. But in this work, we'll be focusing on just the orientation of the potential. And I will define the slope difference as the parameter like capital delta or the triangle there as the dot product like n1 dot n2, where n1 is just the direction of the unit vector pointing along the line in angle space, and n2 is just the direction of the unit vector pointing along the line in frequency space. So the general procedure that we are going to do is first we will just pick one fixed potential, and then the second we will try to rotate all the particles into another frame of reference with the pole located at location L and B in galactic latitude and longitude. In this new frame of reference, we will try to compute the n1 vector and n2 vector and compute the slope difference. I will repeat the process for all the possible new pole locations until we find the location where delta is minimized. So because we have to do a bunch of rotation and dye detection and computing the slopes, we have to find a way to automate the process and return into half transformation in order to do this. So we have to use the half transformation in 3D, but I will start by explaining the half transformation in 2D just to get like the general idea of what it does. So the idea of the half transformation only rely on the equations of the straight lines. Like in 2D, it only have two free parameters, like the slope and the y-intercept. And in this case, the two free parameters are just r and theta, which is r is just the distance of the line from the origin, and theta is the angle that that line makes with the x-axis in this case. So the idea is that at each data point, we'll try all kinds of lines that go through that point by varying the value of parameter theta. And for each data, we will record the value of r as a value pair, and we repeat the process for all the data points that we have. And then finally, on the bottom right, if we plot like the 2D histogram of all the r and theta value pair, we should be able to find like a peak in this subspace, where the peak will correspond to the a line in real space. And if we have multiple lines, that should be just like a bunch of local maxima in the r versus theta space. So the next thing we do is we try to generalize the half transform into 3 dimensions. And in this case, the equation of line in 3 dimensions is just given there, where the first term on the right-hand side would just be the x, y, and z parameter, which is just like arbitrary point along the line. In this case, I would just pick it to be the point closest to the origin. So we have 3 free parameters there, and then t is just like a scalar, and then mx and y and mc is just basically the direction of the line. And it has to be a unit vector, or we require it to be a unit vector. So that takes away 1 degree of freedom. So we have 2 free parameters for the mx and y and mc, which I will just use theta and phi in the spherical coordinates to determine the direction of the lines. So it's the same idea as in the 2D case, but in this case, in the half transform subspace, we have to find the maxima in 5D space instead of in 2D. So yeah, now we'll turn into our data of simulated stream. Like in this case, I will go through it rather quickly because of the time constraint. This stream, the average distance from the sun of the stars along the stream is only around like 50 kpc. And the orientation is very similar to the Sagittarius, like in the XZ plane. And the fixed potential model that we use is just the axis symmetric multiple potentials that another person in our group has been working on, which with separate baryonic and dark matter components up to L equals 4. So here's the result. So I have to explain like all the dots that you see there are just the new pole location that I rotate the particles to. And the color of the dots represent the slope difference, or the delta in that case. And the value of the color bar goes only from 0 to 4 degrees. So that will tell you about the precision that we have to do in order to detect the slope difference. And the cross mark there in red is just the real orientation of the minor axis in this particular simulation at around 50 kpc. So we see that the location where the bright spots are aligned pretty nicely with the location of the real minor axis in this case. Now I will go. This is just preliminary results from Sagittarius stream. We use the data from Eugene's paper in 2021, like earlier this year. There are only like 4,000-ish stars with 60 measurements, but we are limiting ourselves to just like 600 stars in the leading arm, or in the location where C is greater than 0. And in this case, we haven't tried all kinds of potential because this is still pretty new. But yeah, I will make sure to try the prolate halo potential. But right now, what I have tried is just the 3 components, the bulge, disk, and halo, consistent with the Milky Way potential 2014 from Galpai, with varying the values for Q, or the flattening parameter of the halo component. So I try different ranges of Qs from 0.7 to 1. And what I'm going to show first is the distribution of the slope differences for each Q. So in this case, we see that if we pick Q equal 1 or like perfectly spherical, there's no location where it does a good job. Whereas I think like if Q is equal to 0.8, it's doing a better job where there are locations where the slope differences are pretty small. And this is the same plots that you see in the simulated case. But I haven't come up with like a concrete idea of how do I use all this data to pinpoint the minor axis in this case. But just by eyeballing it, I would say in this case, if Q equal 0.8, I would say the minor axis would be around like L of like 45 and latitude of like 15, 20, something like that. But yeah, this is where I'm at for this project. So any questions or comments are very welcome.
Thank you.
Very nice. How about multiple streams? Have you started trying to test on multiple streams yet, and how's it going?
Yes, because I just developed the 3D stuff like very recently, so I haven't looked too much into other streams, but I try another stream where there's still like a bound part, so it does not give like a as good of a constraint compared to this one, because I think I have to remove the bound part first before I do this, because I think I need to use the stars where they don't feel self-gravity in order for this method to work well. But yeah, that's still something that I'm still looking into.
Yeah, so from previous studies, we also have evidence that the flattening of the halo also changes significantly from inside to outside.
Right.
So how degenerate is that with the change of the orientation that you're probing?
Yeah, in order to constrain that, we have to try this method on multiple streams, because for each stream, it will just give better constraint at the location where most of the star particles are. Like in the one that I showed, it was only at 50 kbc. So if we have streams at like 100 kbc, and we can also use it to constrain how twisted the diameter halo is.
So we're just waiting for LSST to come online. That's what we're saying.
Basically.
Cool.
Very nice. So what potential of the halo did you choose for this exercise?
You mean for the Sagittarius stream?
Yeah.
So I just used the 3 components like in GauPy.
Okay.
But so the bulge is just spherical. The disk is like the Miyamoto, and then the halo is also just like the NFW with varying flattening parameter.
Okay.
My brain lit up when you said LSST. Do you need do you need to is there a way to do this where you don't need velocities? Because if we LSST is going to find like all the streams that are in the halo, but we're not going to have kinematics to get action angles.
Right.
So is there a way to do this without that?
I don't think so. In this case, because we need full 60 phase space information to transform to action angle space. So Adriana might be able to help you with that. Right.
Just a comment on this for our future dynamicists in the room, so the whole of the front half of the room. Yes, Alex's point is very good, but so I think the figuring out how to get those radial velocities, the Gaia proper motions will still be useful. LSST will have proper motions. And so the way to think about it is, let's find a good distance indicator. Let's get a spectroscopic survey going, and then use the proper motions from LSST, et cetera. And we hope we're going to push this. But this is your generation's problem, so take it on.